Hi everyone, my name is Shamika, and in this presentation, I'm going to describe how the LCPC transform can precisely measure finger and knuckle shapes for the purposes of studying rheumatoid arthritis in the hands. First, we'll begin with a brief overview on what rheumatoid arthritis, or RA, actually is. Rheumatoid arthritis refers to an autoimmune and inflammatory disease where the immune system mistakenly attacks healthy body tissue and consequently causes inflammation. Specifically, it attacks the lining of the joints or the synovium, which then causes the synovium to get thicker and makes the area around the joint swollen. This explains why patients with RA often have difficulty moving their joints. Its exact causes are still unknown, but a lot of research is being constructed to aid the effects of this condition, since over 14 million people around the world suffer from RA. Women are actually 3 times more likely to develop RA, generally between the ages of 30 and 60, compared to men, who typically start to see the onset of RA after 45 years of age. One significant characteristic of rheumatoid arthritis is the twisting, swelling, and stiffness of joints in the hands, knees, and ankles, with symmetric progression, so signs in both hands, both knees, and more. More often than not, RA begins in smaller joints, and some researchers have even brought to light that the middle finger is particularly useful in tracing the progression of rheumatoid arthritis. So here's a picture of the hands of a 35-year-old patient who has early stage RA. We will focus on the fingers from the left hand, in particular the index finger, middle finger, and ring finger. The purpose of this project is to generate phantom gradients of finger and knuckle shapes based on these real fingers and see how the LCPC transform measures shapes that the human eye cannot objectively assess. But before we begin, let's discuss how the LCPC transform works. In step 1, an outline of a finger is created. In step 2, we overlay a parallel grid system spaced every 5 pixels. The origin of the lines is a baseline represented by the dotted line. In step 3, this allows us to calculate the distance from the baseline to the intersection of the parallel grid and the edge of the shape. After that, we have an option to linearize the data if desired. If a grid line intersects the outline of the object multiple times, all the distances on that grid line are summed into one value. Finally, in step 5, we perform a fast Fourier transform on the data from step 4 to create a frequency plot that is a multidimensional representation of the modic shape. In step 6, we have the option of creating an index that turns the frequency plot into one scalar value representing the shape that we started with. Now, first we'll start off by discussing individual finger gradients. So let's focus on the index finger. I started off by tracing the index finger of an early stage RA patient, which can be seen through index finger 4 in the middle of the top row. Then I created a gradient of 7 fingers by only varying the width. This mimics the swelling of the joints, a common symptom throughout the development of RA. This gradient allows us to be objective in our conclusions because the length of the finger, as well as the general finger shape itself, is kept constant throughout this process. The only variable changing is the width, which can then be seen as a source of any differences we note. The frequency plots show how the LCPC transform sees each of these fingers. From a bird's eye view of the frequency plots, we see two distinct patterns of the 3 middle peaks in each plot. They are represented by either the green outline or the red outline. This shows a recurring theme when the LCPC measures a precise gradient of similar shapes. That is, there are equilibrium states as exhibited by the red peak patterns in fingers 5 and 6, which are invisible to measures of area and to the naked eye. Later on, I will calculate precise indices based on the frequency plots to capture shape differences in these fingers. Here, I wanted to qualitatively illustrate patterns evident from a bird's eye view. We follow the same procedure for the middle finger, starting off by creating a general gradient of 7 based on the middle finger, which is finger 4. For these middle fingers, we see 3 qualitative patterns of the middle peaks as outlined in green, red, and blue. Since the gradient represents a linear change in width, this qualitative pattern is a bad index because it does not match the linear change we see. Later on, I will show you a precise index that matches what the eyes see. Lastly, we ran through the same steps for the ring finger. Once again, the real one is finger 4. Now that we have seen the frequency plots of gradients for all three fingers that we started with, let's discuss a few indices that we created to quantify shape differences in these fingers. Our first index, which we call index A, is obtained by dividing the value of bin 2 by the value of bin 3. For the index finger gradient on the top row, this index A shows a linear increase as the fingers get thicker. Meanwhile, for the middle finger in the middle row, index A exhibits a logarithmic increase as the finger thickens. For the ring finger in the bottom row, index A exhibits a counterintuitive logarithmic decrease as the finger thickens. With this index, a very interesting pattern is that as the fingers get thinner, there appears to be a distinct shape state of thin fingers, which can then be observed in the dotted line boxes. This has important implications of how we develop morphology-based diagnostic models for hand conditions in the future. We need distinct models for male versus female hands and age-specific hands, since these factors correlate with finger thickness. When we compared index A of the three real fingers that we started with, we see that it quantifies the shape difference of each finger distinctively through the naked eye, though the naked eye has a hard time objectively quantifying what it sees. This is the type of precision that the LCPC transform provides compared to other spatial methods. Next, we wanted to determine if we can measure knuckle shapes apart from their fingertips, since rheumatoid arthritis affects the morphology of joints first in its progression. We derived a gradient of knuckle shapes by systematically removing the fingers from the finger gradients that we previously analyzed. We defined the cutoff point to be midway between the two finger knuckles as shown by the red lines. As you can see in the frequency plots, removing the fingertip simplifies the overall shape of the frequency plots compared to the whole finger shapes. We did the same for the knuckles of the middle finger and the knuckles of the ring finger. We then calculated index A that was previously mentioned for whole finger shapes, which is to divide bin 2 by bin 3. For the index finger and the middle finger, which are the top two rows, we see linear or logarithmic increases as the knuckle thickens. But for the ring finger, which is the bottom row, we see that the thickest knuckles exhibit a distinct shape state. When examining the frequency plots, we also derived a different index called index B by summing the values of bins 2 through 6. Index B quantifies the gradients of the index finger and middle finger well, as seen in the top two rows, but not the ring finger, which is the bottom row. Next, we compared both index A and index B across the three real fingers that we started with. As you can see in the top graph, index A is good at quantifying the shape of the knuckle on the index finger apart from the other two fingers. And in the bottom graph, index B readily distinguishes the shape of the knuckle on the middle finger apart from the other two fingers. This is exciting to us because it shows that we can precisely quantify knuckle shapes through images that can be taken from a smartphone camera. Let's discuss some takeaways from this project for future studies of hand images for rheumatoid arthritis. 1. We should start by collecting a large sample size to capture natural variation of finger and knuckle shapes. 2. We should create age and sex-specific standard shapes to control for natural factors that affect finger shapes. 3. We then have baseline values from which to measure changes caused by early stages of rheumatoid arthritis and osteoarthritis. In conclusion, 1. Fingers can be categorized into distinct shape states based on results from the LCPC transform. This means that future diagnostic models need to be age and sex specific. And Two, knuckle shapes can be measured apart from finger shapes. And then this takes us to three, where the LCPC transform works with images of hands taken from a smartphone camera. So, for those who are interested, we have a video on how the LCPC transform can be objectively measured, um, can objectively measure the shape of left versus right hands, which is something that area and volume cannot. Visit the use cases pages of our website at www.brainscanology.com. This brings us to the end of the presentation. Thank you for your time.